Yeah, you already. Okay.
Okay, so we begin the second lecture by Timur. It's going to be on collisions.
All right. Hi, everyone. Good morning. So, yeah, not so many expressions today, hopefully. So we'll be talking about molecular collisions, and all the information I'll be talking about is taken from these three great books. Joanne already mentioned, there is no their book, but of course their book is always implied in the background. Like so this is the child book is kind of like this from the 70s. So it's the really foundation of molecular collision theory on all these rotational states and everything. So this is more like a newer one, 2018, which has a lot of useful chapters. So it depends on what you want. If you want to collisions without external field jets and field free space, there's a chapter on that, and that's called chemistry book, but there's also a chapter on collisions in external field. So, and then there's a book by Roman Krebs, which John mentioned, which has also aspects of that collision physics. Okay, so, all right, so John is back, so let's move on. And we'll just begin from the basics, right? So here, basically we wanna, we treat in this lecture the process of two particle collisions. So we basically define the center of mass coordinates. And you may remember that from your quantum class, quantum 2 especially. This is where we treated two particle collisions, right? It's a quantum two-body problem, in other words. So fortunately, center of mass is easily separated out, and you can define the relative velocity, the relative position and relative velocity, and then you can write kinetic energy in terms of, center of mass motion and the relative motion. That's all fairly standard, right? But in this is actually quite non-trivial to do the transformation, actually, if you're in as far as experimentalists go. So this is so-called, they use this Newton diagrams, and you might have seen them before. So this is basically the velocity vector diagrams. When you have the two particles in the lab frame, they have velocities pointing in some directions, right? But then the center of mass frame depiction is quite different, right? Because there's center of mass velocity, and then there's this relative velocity. So you draw this triangle, and then you draw the relative velocity, and then you find your position of center of mass, and then you calculate basically what matters is in the lab you measure, right? So the thing is that you measure these distributions of scattered quantities in the lab, and then you transform them into center of mass frame. Or you can do the other way. So you start from center of mass distribution, then you transform it to the lab frame, and you kind of solve the inverse problem. And that's actually not trivial in molecular beam experiments. So I'm not an expert in molecular beam experiments, but I remember sitting in the same office like the molecular beam experiment was frustratingly transforming their results, to the lab, to the center of mass frame. And actually, it's not a trivial process. But for theorists, basically all we do is we actually work in a center of mass frame. And so we basically can transform them forward. So if we have any theoretical results, we can transform them to the lab results. And then I'll show you some examples later in this talk how this is done. But generally quantum mechanical observables associated with collisions are three main observables. Differential cross sections basically gives you the flux of particles. You think of it as a collision, again, this is graduate level quantum physics. So there's a flux of quantum mechanical particles, right, hitting a target, and then debris are flying in all the directions. And you measure how many input detectors around it, and then you click, the detectors click in different directions, they click at a different rate. And that's how much stuff is going in that particular direction on the solid angle theta and phi, right? So that is pretty much, I took it from the child book, but it's in Koen-Tanuji as well. So it's in your favorite quantum mechanics textbook. So nothing new here, nothing really fancy. This has been known from the 30s. So it's almost like 100 years old stuff. But what we also need, we'll need the integral cross section, is just like how much stuff is scattered in all directions, right? You just integrate over all angles in the center of mass frame, but also oftentimes when you have an experimental setup, what you measure is not the integral cross section, because for that you have to fix the energy, the relative energy of the collision, right? And that's not often available. It's usually done in molecular kind of molecular beam experiments, but in the trap experiments, you have an energy distribution, right? And so you integrate over trap energy, like all the different kind of velocities of collision products, relative velocities. And then you typically know this distribution from some, modeling maybe, or you just assume Maxwell-Boltzmann distribution often. If it's a thermal gas, of course, if it's a PEC, it's a different story. You just basically plug in your favorite P of V function in the distribution, you average it over it. So that's the collision rate at the temperature. So so if you know, basically the most fundamental quantity from the scattering point of view, theory point of view, is differential cross-section. You have differential cross-section as a function of angles, you can calculate everything else. But let's say if you have a rate constant, it's highly averaged quantity already, so there is no way generally to extract the cross-section, except that you as you're in ultra-low temperatures. So this is something called, Wigner's threshold laws, and I will not cover that in this lecture, because this lecture is most about general quantum molecular collision theory rather than ultracold. I'll mention ultracold quite a bit, but it's not specifically about ultracold, because it's more general. So what do we deal with here in scattering theories? We care about wave functions, right? The time-dependent independent Schrödinger equation. And if we can solve it subject to this boundary condition, right? So this scattering wave function, there's incident wave function, sine tilde, and then there's scattered flux, and this is just the spherical waves going all directions with different amplitudes. Actually, amplitudes are called the scattering amplitude, f of theta. Again, a fundamental quantity. Again, it's quantum 2, quantum G, beginning of second volume. So, it's a time-independent way of solving the scattering problem. There's also wave packet techniques, which we will not talk about today, but you can actually solve time-dependent Schrödinger equation if you want. But for ultra-low temperatures, normally, this is kind of the preferred technique of solving the Schrödinger equation. For some reasons, I'm going to go into it. This has been the way almost everyone was solving the scattering problem in ultra-low temperature. So you define the flux as a usual flux operator, and for example, flowing wave, calculate that it is response to a particle moving in the direction of z direction in a certain velocity, right? It depends on de Broglie relationship, like a quantum mechanical de Broglie wave just moving along the z-axis. So it's moving on the target, and then it hits the target, and then all the flux outward far away is spherical, right? And then you measure the scattering amplitude. The scattering amplitude is the fundamental quantity. That's a differential cross-section is just square of the scattering amplitude. So I should say here, there is lots of information as you calculate, as we discussed before. So it's kind of doing averaging. Right? So the most fundamental quantity from a theory is called the scattering amplitude, because it's a complex function generally, and it has pools and all kind of interesting analytical structure in the complex plane, which when you take this differential cross-section, you actually wash it out. So the phase information is washed out, but actually it's quite interesting that the ultra-low temperatures, maybe some detailed experiments now are able to maybe even access the phase of this. That will be actually quite interesting, which a new direction in the field, which I think some people are thinking about, as far as I'm aware, and we have been thinking about this as well. So in other words, if you know the differential cross-section, you cannot generally back out the wave function from it, because you have done this square after you lost the phase information. So, right? Okay, so, but still, if you know the differential cross-section, you know pretty much a lot about the quantum scattering process. And so we go from one to many channels now. So now we're going into molecules, right? So molecules have a complicated structure we talked about yesterday. So let's say we have an atom molecule system. Atom is hitting a molecule, right? Quantum mechanically. You have the Hamiltonian, which is like relative kinetic energy plus relative angular momentum, or the angular momentum plus H1 and H2 are the Hamiltonians, internal Hamiltonians of the atom and the molecule. Now there's B12 of R and Ri, the interaction between the two systems, right? So the interaction is a general operator here. It can depend on spin degrees of freedom, actually, and it does sometimes in general cases. It depends on both spin degrees of freedom of the total system of the molecular collision complex, as well as the orbital angular momentum projection on the some axis. Right, so you can write it like that, but typically for simplicity, we will not consider that dependence in this lecture. We'll just assume that it's a scalar function and it's like spin dependence, only spin dependence. So we're talking about collisions of S state, sigma state. Also, there's no orbital angular momentum, so it's like spherical symmetric, and only spin is involved. And S is actually not the individual molecule spin, the S1 plus the total spin of the spin. Well, you can extend the potential like that, but even if you have like the even simpler cases where spin is not involved at all, there's like maybe one potential energy surface, right? And this timing system, and then your spin is equal to just is fixed. So you can just drop those spin as sigma projectors onto the total spin basis function. So, but this is the general form of the potential. So if you are to, you can go to basics and you feel like you need a more thorough treatment. You can always go back to that. So the then, once you extend the wave function in some basis, channel basis, and we'll come back to that. So, and then you combine it with the Schrödinger equation, and then you do some math after that, like projecting it out, and basically you can derive what is known as coupled channel or close coupling equations, which are actually the central, theoretical tool or the key theoretical tool of independent quantum scaling theory. And of course, not specific to molecular physics, right? These equations actually were first derived in the nuclear physics community in the 50s, I believe, or like maybe 60s, I would say. So, and then people actually started investigating them, and most of the theoretical science was actually due to nuclear physics community. And then molecular physicists kind of like jumped in and they took advantage pretty much of in the 70s of this vast nuclear physics literature. And except that, okay, so nuclear physicists were not in a privileged position because their interactions are very complicated and generally not known. But the beauty of this formulation as applied to molecules is that we know actually most of those terms in the Hamiltonian, or we can calculate it, as we discussed before. Nuclear physicists don't have that luxury. So this field was very rapidly developing in the 70s, and people were deriving, yes, John?
What did they do before?
Molecular physicists?
Yeah.
Well, they use some classical pictures, like solving trajectories and things like that. So the field of molecular collision theory really, I mean, this child book is early 70s, and I think most of the development occurred in the 70s. So, and in fact, like even if you can write them down, those equations, there was no computational power in the 70s to solve them. You can write them all you want, right? But unless you can solve them, there's no use. So people derive them and so they solve them for really simple systems like 10 channels or model problems. One-dimensional collinear, there was like a decade where people only will solve like collinear problems because they couldn't do three-dimensional scattering because it was so computationally intense. We'll come back to that. Why is it so computationally intensive? But well, pretty much it's very similar. There's zillions of those files that you have to include in order to produce converged results, or numerically exact results. So, anyway, so these are the equations. You see, just let's dwell a little bit before we move on. So here there's derivatives. So you have to take it's a remnant of kinetic energy operator here. The relative kinetic energy of two colliding molecules is this term, plus energy, the incident energy. So this collision energy, because you launch them, right, initially. So that's like your part of the Hamiltonian that comes from H psi is equal to E psi. Right, so this is that E precisely the collision energy you start with. Because remember, it's a problem you start in the continuum. So you starting your molecules at any energy. You can do them starting at any energy. Energy is not contact, right? So it's in the continuum. So on the right hand side of the equation, so there's this f alpha is the expansion coefficient. It only depends on the distance between the molecules, and then the rest of the coordinates are kind of like tucked in this R hat and R sub I. So this is like all the rest of the coordinates. So the beauty of this formulation is that you explicitly separate the continuum, which is where the particles can go to infinity essentially, from the rest where the particles can only undergo finite motion, right? In other words, or quantized motion. So this is like continuum nicely separated out. This is the continuum function, and the rest is all the bound state functions, right? So, and then you can take the matrix elements with respect to the bound state wave functions. They're not going to diverge at you, right? And that's another advantage of that, because otherwise you cannot take matrix elements normally with respect to function, because these guys do not go to zero, and as R goes to infinity, they actually oscillate. And from these oscillations, you can extract information about scattering. That's kind of the long and short of it. But technically speaking, in order to solve the scattering problem, right? So you have to actually set up the matrix elements of the Hamiltonian, again, coming back to this Wigner-Eckert theorem and angular momentum algebra. You won't see much of that today because I assume you already know all about it from yesterday's lecture. So we're just gonna go over these terms. And so you have to calculate the matrix elements of the internal structure, H1 and H2, and the relative orbital angular momentum, because now the kinetic energy has not only the radial term, but also they can orbit around each other. So there's like there's angular term. You have to calculate the orbital angular momentum. Fortunately, at ultra low temperatures, it's almost always zero. So you don't have to deal with it all that much. You still have to deal with it, but with a few values only, because you're well controlled, the relative motion. But still, these guys can escape to infinity, right? So you have to worry about capital R. You have to worry about all these internal potentials, so internal Hamiltonians, H1, H2. We covered them yesterday. So H1 and H2 is like what happens inside the molecule, rotational structure, spin structure, right? We know all about that. Yesterday I showed some energy. These are the energy levels of the colliding molecules and atoms. But V is something new. V12 is like, again, the interaction. You have to calculate, take it down the interaction. And the interaction is something quantum chemists give you if they, are kind enough to you. They can provide this kind of potential, and then they have to feed the potential. So like a whole, process. It's a very tedious and important process where you calculate this whole. The current structure problem yesterday is actually we touched on this subject a little bit. And you get this function. It's actually a function of many coordinates. So not only do you have to calculate it, you have to fit it then, and then you have to actually write it some sort of code and then hand it over to them. And this is what the essence of collaboration, like in the theory world, of these two camps. One big camp is solving this for V's, they're called quantum chemists, and the other quantum dynamics people who do the rest, essentially. So that's people like me. So I don't really, and I respect those people who calculate these V's because we'll come back to that point. There is uncertainty in them, and actually, except for the V, the system this is exact. So there's no approximations involved. So far, we've just been solving the Schrödinger equation, right? So the only uncertainties actually can come due to V, and they do come rushing in quantum scattering calculations. And this is one of the actually main problems currently with the field, and to account and minimize uncertainties in these potentials. So anyways, this is just one example from +1 dimensional of how this works, right? So basically you calculate the integral, you can solve the coupled channel equations, and you can calculate the integral cross-section as a function of collision energy. And they look like this typically. So they have these peaks, which are called scattering resonances, and then you can actually use those differential integral cross-sections to reconstruct the experimentally observed, for example, velocity images and profiles. So you basically solve the, you go to the lab frame with your calculated center of results in the center of mass frame, and you compare, and you see that the results are excellent. For this kind of system, and no plus helium inelastic collisions, actually the potentials like these guys, these V12 are so accurate. You can do them so well. The uncertainty is so low that you can actually obtain pretty impressive agreement with the experiment. So, and that is, kind of like, perhaps the pinnacle of molecular collision theory, when you have a very satisfying agreement of all inelastic collisions. And so, there are groups in the Netherlands and theoretical collaborators at the University of, I think, Nijmegen. They're doing an excellent job at that. Yes. So in the upper part, when you show me the cross-section of the function of the helium, yes, exactly. And no and helium in this case, just like relative kinetic energy. Right? Oh, there are resonances. So cross sections go up and down, and each of those resonances they correspond to some kind of motion in this collision complex. For example, some trapping current barrier. So there's some understanding to be done there. This is just illustrative. This one for the purpose, like just it can be done, right? And theorists are very good at treating these kind of systems. They have become, so thanks to the efforts of many theorists. It didn't happen overnight, and it didn't happen free of effort. It was a huge effort to get this to this point that and agree. And so it's very satisfying to me personally as a theorist. There's a lot to do still in the field because these are helium. Helium is a weakly perturbing atom. Collision is pretty weak, so it doesn't really perturb any molecule when it collides with it. And no kind of like, okay, I saw some helium, it came and that induces some perturbation in my rotational energy levels, and I get some bump, but it's okay. But let's say we look at KRB plus KRB, that's another way. It's like intruder coming in and destroying you completely, right? The molecules get completely destroyed. And you have reaction product as observed in Kanko's lab, right? So it's different. This kind of different interaction, right? They can be very gentle, like in this case, or can be very rude and destructive, like in the case of when the chemical reaction happens. And the chemical reaction is, the example is like ultimately inelastic collision, perhaps, where even the molecular identity is changed in a collision. The collision is such dramatic event that the molecule in this case doesn't survive pretty much. A new molecule is born, and the old molecule is gone, essentially, right? So there's different kinds of collisions, right? Reactive, inelastic, and again, as these are, like I said, this is. I think the dots as a model that uses resonances as a model for S matrix near resonances, which is used here in this case to prove that this is indeed the resonance contribution to the scattering cross section. Yeah. So, this is just to show you, what can we potentially achieve if we have this full quantum scattering calculation. So, complete picture, full S matrix, no approximations, right? So that's the goal of everything we do, actually. But achieving this goal has proven to be a difficult task, right? So, but before I will explain you why in a second. But I just want to give basically give homage to pioneers in the field. Who's actually and most of the rest of my talk will be on the effects of external field on molecular collision, because it's such an exciting development. You can actually try to use the external field to control and to induce resonances and do all kinds of interesting things with collisions. And John Born, who is in the audience, is the first person I know who thought about including effects of external magnetic field in this case in atom-molecule collisions. And when the second person was Roman Kranz, who was my advisor, my postdoc advisor, and who wrote this book, the green book that I was showing on the first slide. So what they figured out is that if you can define the basis functions, and these are they picked a very nice, so they picked very nicely those functions apart. And they picked them to be direct product of internal states of molecule A or atom or molecule B, number 2 or B, and then times the partial waves of the relative motion. So this is a fully uncoupled or direct product, the tensor product basis set. And the advantage is that it actually has very simple and straightforward expressions for the matrix elements. Because you see, because L sub L, angular momentum for the relative motion is separated here, the matrix element of L squared almost trivial. It's just like diagonal. Everything is diagonal in this basis. And it's very satisfying. So I was a graduate student when this paper came out, and I immediately realized that this is what I wanted to do. So, and I started doing that, and in a way, I was in a very good position. So the field was just taking off, and basically, programming was easy back then. In this basis, everything was easy, and it felt life was good, and it would, things will, using this basis, we could go places and do a lot of calculations and treat, basically solve all collision problems out there. But life, it's best because it's still very used. It's actually still very widely used in collision physics because it's easy to just program and calculate the matrix elements. It's very. Yeah, but I'll get to that point in a second. Yeah, I'll get to that point. Why it is expensive and what can we do about it, right? So that's what the next chapter. But at that time, everyone thought that this is actually the best basis set, and everyone should use this basis set. And as a postdoc, I went to University of British Columbia in Vancouver, and I started just churning out, applying to all kinds of collisions this basis set. And it took me several years to realize that something is, it's not perfect, to find the imperfections in the basis. And let me now point out some limitations. So because the interaction potential, depends on this angle, theta, right? So actually, it's not interaction anisotropy, and it's a very, very important feature of molecular collisions or atom-molecule collisions, because in atom-atom collisions, generally the interactions are isotropic, so they don't depend on the direction you look. But in the case of molecules, they do, and they do that extremely dramatically. So, for example, in one place, if you have theta equal to 0, and some typical atom-molecule collision complex, I'll show you some examples in this lecture, you can get minus 100 Kelvin or deep potential. But if you just switch theta a little bit, go to T-shape configuration like that, you might get 2,000 Kelvin. So it's like a steep hill, in other words, and you're skiing this down the angle. And then this and different L values, they don't like that. So these different L are coupled by this interaction. And if you are to actually if you're dealing with anything other than helium or neon or weakly anisotropic systems where this dependence is very weak, the number of basis functions is way over 100,000. This is what I found when I was a postdoc, and I was very depressed for a while. so I thought that, that was it. Because you can also currently, because this computational scale will go like n cube with a number of channels. It's just like the methods that work, they work with matrices. And matrix operations like inversion, diagonalization, they go like n cube with the dimension of the matrix. Unless you have sparse matrix, but these matrices are anything that's sparse. So, and I'm looking at, if we just include 55 L states, which is not untypical, sometimes you have to include hundreds of these guys. And 55 rotational states, which are also coupled by the anisotropy of the interaction potential. So you're looking at millions, 100,000 at the very least. The maximum we can do at present is about, depends on who you ask, but I did a calculation with 18,000 channels, and it took like half a year just to do like a single point. We're just like exploring what can be done, but that was like 10 years ago. Now I'm sure you can do maybe 25. But still, it's far cry from what you would need to treat even a simple molecule system like Li plus calcium hydride. So fortunately, I went to ITAMP, where it was Alex Delgado, and I started reading kind of his papers and talking to him. He is a great scientist who really founded the whole field of molecular collision theory by just publishing a single paper in the 1961 with Arthurs, where he figured out, okay, if we cannot use this basic, he actually probably had a similar problem, but it was back in the 60s. But so he actually figured out that if we can define the total angular momentum of the collision complex, and because rotational, like angular momentum corresponds to rotational physical system as a whole, as opposed to different parts of the system moving independently. So, and because there's rotational invariance, right, of interactions, like general potentials, they don't care, right? If you rotate the whole atom molecule system, like atom and molecule like this, or this, or this, it doesn't care. It only cares about this angle, about the relative orientation. So similar to like if you have a Coulomb interaction, right? If you rotate the whole system as a whole, the molecule and atom doesn't change interactions, right? Fortunately, right? And this is called rotational invariance. And in quantum mechanical language, it means the total angular momentum commutes with the Hamiltonian, right? And also its projection also does commute with the Hamiltonian. And so this is what Alan figured out for molecules. And however, there was a problem because we had external fields. And external fields do not generally conserve total angular momentum, right? As we know, rotational invariance, because they define a direction in space, and John mentioned that yesterday, we have a quantization axis. And because of that, only J sub B, the projection of angular momentum on that axis. And obviously, rotational invariance is broken. The rotational symmetry is broken. And it took me a long time to, like, there was general pessimism at that time in the field of using this total angular momentum basis, because, like, for example, my advisor, Roman Kranz, told me to forget about it. But I was so desperate that I actually, to get these calculations done, so I actually tried it anyways. So I said, to hell with non-conservation of angular momentum, let's just do the computation in the total angular momentum basis anyway, and see what happens. So, well, so we defined, and, it was back in 2010, and I wasn't sure that it would be successful. So I just defined this basis set, I put in some angular momentum. Because external field was there, I had to actually couple different total angular momentum states. So that was never done before up to now, and people said that I was crazy, so I shouldn't do that. And they were wrong, hopefully, fortunately. So if I include this, so basically all these interactions, so the beauty of this total angular momentum representation is all this strong interaction that I just mentioned as anisotropy, not a molecule that cut in the total angular momentum blocks. Because there's no coupling between the states of different total angular momentum, so you can neatly arrange your matrix in such a way that only J equal to 0. You only have to solve J equal to 0. Ideally, at low temperatures, right? Because that's one of the lowest partial wave. It's not truly a partial wave, but for our purposes, it still is. Interaction anisotropy is all packed in, all neatly in these blocks, but magnetic field is unfortunately, or electric field, goes out and couples different total angular momentum states. However, fortunately for us, that didn't turn out to be a huge problem, because actually these couplings between magnetic fields are very weak, and the green couplings are like thousands and 10,000 times stronger. So by putting these couplings and using the symmetry, you actually not losing much, and you can include a few of these total angular momentum blocks, and you can demonstrate that convergence happens to the exact result by just including a few of those total angular momentum states. That was unexpected. And that actually allowed us to do calculations that, for example, our experimental colleagues were asking us to do because they had double sigma molecules and they were interested in if you can do a sympathetic cooling of these molecules or perform sympathetic cooling, meaning that you mix the atoms up with very ultra cold atoms, and the molecules are not so cold. Well, maybe the hope is that the molecules can be cooled by elastic collisions, or thermalizing collisions with lithium atoms. And this was, we calculated, fortunately I had a friend, Jacek Pros is a good friend of mine, who calculated the potential for me. It was hugely anisotropic. It's impossible to converge using the uncoupled representation. But so we tried it on it was a good opportunity for us to try the new basis that we developed. And just to understand the potential uncertainty here, it's in linear geometry, Me is like metal, it's like lithium. In linear geometry, it's about, you see 140 wave numbers, but in the deep minimum, it's like 6,500. So as you change the angle, you go a factor of like 60 in the interaction, essentially, right? So it's crazy. So I figured out in the normal representation people used before, you cut these 234,000 channels, which is just ridiculous. I just put it in the paper I tried to get a PRL. So basically, I wanted to impress the referees, so I wrote, but the referees were not impressed. So they said it's not a PRL because it's, Anyways, this is another thing that I couldn't impress, right? It ended up as a fusor of A, which I'm pretty happy about. But you see, this is how much rotational space you can include. Many you can include in the basis to add. You need a convergence. You need to do 55 rotational states. But you see, the red line is the maximum you can do with the uncoupled basis set. So here, you see how the total angular momentum representation allows you to actually achieve converged results, numerically exact results, by cranking up the number of rotational states up to where actually you need it to be in order to get, numerical convergence. And if in case you're wondering what numerical convergence is, it's basically you have to saturate the basis set, right? You have a basis set and you're increasing it, your results do up and down, right? What does it mean? Your cross-section is not fully converged. It means that your cross-section is rubbish, pretty much. to be like, precise. You might as well just throw a coin, gamble, and you see, you would probably get a good, you get a good guess. But so you're not solving a Schrödinger equation once you crank it up enough so that the result no longer depends on the basis set. That is when we start really begin talking. And that is when you're approximating the solution to the Schrödinger equation to a sufficient accuracy to even begin speaking about something useful. But maybe I'm being too strict and especially when I was arguing with people that, you should get converged results at all costs, but sometimes it's actually not required and some qualitative. So if you just want to have a qualitative look, it's probably enough, but you see, you can overshoot that's where your limit, right? And you say, oh, the cross-section is huge. But when you're talking about some important number that you want to get, right? You'd better use converged results, right? And if you just care about, let's say, qualitative tendencies, things like, what is a typical magnitude? You don't care about orders, like 2 orders of magnitude, that maybe you can use a small basis set. So that's fine. And it's like in electronic structure theory, there is complete basis set limit. It's similar if you're an electronic structure minded person. They talked about for ages about things that's called complete basis set limit, which is the fully saturated exact limit, which can be achieved using this angular momentum representation of Alex Delgarno developed in 1961. So, and then, this is some result that we achieved with this back in 2011 with this basis set. And we saw, for example, that the inelastic ratio, the elastic to inelastic ratio is pretty large. And so that means that sympathetic cooling of calcium hydride with lithium is likely to be successful. I'm saying it's likely because these results still have dependent on the interaction potential, because the interaction potential is not perfect. The results can be different if someone measures them. And even if you converge everything and you've done all this work, you're still not out of the woods completely, because there's this uncertainty in the potential. But anyway, I felt good about it. So we went and studied a lot of systems, and with this basis set, it was like I could have a I could pick any system and study it pretty much. I don't know a system that people couldn't study before. So for example, we studied in Roman terms, this is chemical reaction. We obtained conversion results for it, solved the Schrödinger equation. This reaction actually quite interesting. It's of course a very theorist kind of reaction because it's not very deep potential surface, but it has very. So it's not a kind of insertion reaction that is typical of alkali metal dimers because it's not an alkali metal dimer. But in chemistry, there is actually a lot of reactions that have barriers. And Eric mentioned that in his first lecture. And the dynamics of this reaction does not typically follow the conventions that we're used to, things like statistical universal theories and all that. Actually depends very highly on the height of the barrier, because the tunneling rate obviously is very sensitive, not only to the height, but also to the shape, how thick the barrier is, right? And chemists thought about it for decades, and there's like very ingenious theories like transition state theory, for example, that work. But then also, you know, because everything is so sensitive to the barrier height, if you get it a little bit wrong, and unfortunately the barrier height is very sensitive to electronic structure methods that you use and everything. So even if you get a huge error in the tunneling rate, obviously. That's a big problem with these reactions. But anyway, we had some potential, which had some barrier. So we just wanted to do exact dynamics calculation. And what we found, so we did this. This is some hyperspherical coordinates. I'm just going to push it aside, but this is the most important result. We mapped out the electrical dependence of the scattering cross-section, and we saw these resonances in there, which is actually quite interesting. What's going on? And pretty much this is because the particles tend to tunnel. And again, as Gareth mentioned, there's this allowed windows of energy where tunneling is allowed or more efficient, right? They're called resonances, tunneling resonances. And this is what happens. So at some energy, the barrier becomes suddenly quantum mechanically more transparent to the molecules, and then they go. But at other energies, right, that doesn't happen, and the reaction rate, cross-section is like 0.1 atomic units is like really small. The reaction rate would be like 10 to minus 14 or even smaller per second. So no reaction because the barrier is kind of blocking them, preventing them from it. But at some electric field, and it was cool pretty much. So we thought someone could. Yes. Oh, it's just like there's some bound, like there's some levels where scattering energies. Remember from the Cohen-Tanucci, there is a potential step problem, and there's this allowed energy that let them tunnel better. Well, this is a three-body system, so there's rotations involved, total angular momentum involved, and partial wave involved, and that's why there's splittings. So we can go into further details. It's actually explained in the paper in more detail. So but you can kind of rationalize that. Yeah, but the long and short of it is this is basically tunneling resonance. So why would you keep that approach? It's this. Incident there no there yes, the wave function is localized in the incident channel, but it kind of trickles through the barrier and goes to the incident channel that way around. More chance to come through. I think so. Yeah, they're actually in chemistry. They're not your usual type of resonances. They were discovered actually originally in the absence of external field by Joel Bowman in I don't know, this famous chemist, physical chemist in early 2000s, and they call them tunneling resonances, and we just refer to them. This is known phenomenon in physical chemistry, but I think most of the wave function is the entrance channel, but it kind of goes into the exit channel as well. But this is the point of this is just to illustrate that calculations can be done by solving Schrödinger equation, and interesting resonances can be predicted. Of course, potentials will change that. If you change the potential, and that's my next point. If you change the potential a little bit, you have like huge variation typically. Well, not always, but for many reactions, especially reactions with a barrier, you get this like ups and downs, right? And they span like 8 orders of magnitude, right? So it means that pretty much a small change in the interaction potential, again due to some resonances that become close like to threshold and then reappear, they resurface from bouncy, they become continuum state. And as you do that, the scattering length, of course, diverges and then it converges again. It's extremely sensitive at low temperatures to the details of the interaction potential. So what's the point of doing all of that if you change the potential a little bit? And then, well, there are 2 points. Well, we had some discussions about that and arguments, but I think kind of the conclusion is that if you have an external result, you're trying to back out the interaction potential, you've got to do the accurate calculation, right? There's no way around that. But if you just want to look at rough numbers and do some simple calculation, what we can do, you can average over those resonances, or you can do a calculation with. You don't have to worry as much about basis sets and things like that. And actually, I'm going to illustrate that fact using a simple model, which is called universal/statistical model, which is probably the workhorse currently of ultracold collision physics, right? What does that model say to you, right? When you come and say, oh, there's this complicated reaction, the reactants go in, and typically there's a deep potential well for this alkali metal diamonds, right? There's no barrier. Well, it says, okay, they come in, and there's so many states inside. The short-range interaction is so complicated, which it is, that there is no chance for these, reactants to ever go back and, re-emerge in the endless channel again. So this is called this collision complex / universal model. It's been around for decades, and probably. Like in the chemical physics, there's chemical physics community, there's atomic and molecular physics community, and they kind of like when there's separate ways about this model. But in chemical physics community, which I'm most familiar with, is due to originally John Light, at the University of Chicago, and then David Monolopoulos, David Clary, I think they're Cambridge, Oxford, and Julian Troy in Germany. So and of course, Pechukas was involved. Many people over years developed this concept. And it's a very attractive concept. It says, okay, this short-range mess that causes these quantum scattering calculations to go insane, pretty much, expand in computational complexity beyond any capabilities, right? So that can be replaced by a compact black hole. Okay, and the black hole, what it does, it basically sucks in your reactants. It doesn't give anything back, just because it's a black hole, right? It's very greedy. Okay, what do we get if we assume that? It's a very interesting idea. So ignore short-range interactions, everything. So just replaced by black hole. It was John was one of the early proponents of this idea. Paul Julian with Asiatic development MQDT-based model founded on this idea. And other people, Ivana Hakuchidova, Balakrishnan with the University of Nevada, Las Vegas, Bogao, Toledo, they actually did calculations of alkali dimer reactions using this black hole assumption. And when they did that, they found an excellent agreement between the reaction rate that was calculated and experimentally measured, right? That was a miracle. It actually indicated that all the short-range chemistry can be replaced by just this universal black hole, right? And it was. Okay. Actually, Svetlana Kopachidova and Balakrishnan and Brian Kendrick, they went further and actually did exact quantum scattering calculation of the kind, a couple channel calculations that took them years to do, many years. And they saw very close agreement between the universal model rate, which this plot is, like on the right-hand side, UN is the universal model, and exact quantum mechanics is the black line. You see, there's like almost perfect agreement, which is like a little bit depressing when I look at it, because like you have to spend 5 years doing this complicated calculation, and then some simple model, you can do on the back of the envelope, like in 5 minutes, provides the answer that agrees with it, right? Exhilarating and depressing for people who are trying to spend 5 years doing quantum calculations, which is probably like I was, and it is interesting. So let's talk about the whole concept behind this is this universality idea. And the idea of universality is that you have these complexes that form at short range, and it doesn't really matter once, like we just said, short range chemistry can be kind of incorporated and packaged into this, okay? However, and sorry, before we get to that, the reaction rate expression is important. So you get analytical results for the reaction rate. So for P waves, and I recommend this paper, and I also recommend John's paper with Owen Clemener on this topic. So they both came out in 2010, almost kind of on the same time. when Jill experiment on KRB plus KRB was just, the result just was public. So you see, if you want to calculate the black hole rate or universal rate, all you need to know from a practical perspective is two things. Actually, yes, you have to know the average scattering rate, which is 4 pi R6 over some constant. But R6 is actually all you need to know to get the R6, which is van der Waals distance, is actually the reduced mass of the system and the C6 coefficient, the long range interaction, right? And that's it, right? So the long range interactions are quite easy to calculate very accurately. So Svetlana Kotochigova and actually Andrei Derivianko from UNR physics department, they have extremely precise calculations of the C6 coefficient, like, for molecules, like even big molecules, like triatomic molecules. But so that's all you need to actually plug in the numbers, and you get those graphs. And the graphs, if your model is universal and the system is universally behaving, they will agree. Okay, all right. But oh, what do you mean, like more, a little bit more? What goes into this calculation, probably you're more interested, like the way this is derived is, and this is what I was trying to deliberately avoid it, right? It's so-called multi-channel quantum defect theory, MQDT. And the idea is that basically you separate the short scale range from long range, and then you assume that there is no outgoing flux. So remember this boundary condition that I showed, psi is equal to e to the minus ikr plus psi to e ikr. You just cross out the terms that has, minus or plus, one of them. You basically cross out, you prohibit one flux from ever emerging back from the black hole. When you do that by introducing so-called complex potential or optical potential. And if I had time, I have some notes for you with the derivation, but yesterday I spent too much time deriving things, so we can talk, but it can be derived. And this paper, it has this two effective channel MQDT model that when you do everything, and to be honest, I haven't gone through all the derivations and steps, but this is what they get. But I checked this equation numerically by applying absorbing boundary conditions in my code, and it actually agrees almost perfectly within like 1 or 2%. So I trust this expression. I checked it. But the beauty of this expression is, again, no knowledge of short-range interaction is needed. So any system, no matter what you do there, it's like black hole. No one cares about what happens about black hole, what black hole does, right? At least in chemical or hemophilia. But it's not always the case. Sometimes black hole is not a good assumption. Sometimes things like, for example, effects can happen beyond universality. And this is actually an exciting, like the topic that I'm very excited about. For example, you have a phenomenon known as a Feshbach resonance, right? If you have a Feshbach resonance, obviously a changing magnetic field, something changes, right? And your rate is no longer universal because the short-range interaction change. And if you go beyond the universal effect, you actually have an opportunity to learn something. Because on the one hand, it's fascinating, as John mentioned. On the other hand, it's extremely depressing because it shows that no matter what system you have, they will all have the same rate, right? Like no matter what, RBCS, KRB, sodium, potassium, calcium hydride, the system variability in this system is not that high. So all the rates are going to be pretty same. And we're learning nothing about short-range complex in this way because there's no short-range complex and there's no room for this short-range complex in the model. So, however, I should mention that these kind of results, and it's known in chemical physics community, do not necessarily, and it's important to emphasize, rely on the formation of long-range, short-range complex. So the same behavior can be reached using different ways. For example, so what this really relies on is so-called random phase approximation. So what this requires is that the phases of the S matrix elements are actually quite randomized, completely randomized. And if that's true, then you get this expression. However, that does not require complex formation. It could, but other mechanisms can be at play that do not necessarily involve complex formation that could give you exactly the same rate, which is something something that I think is not often emphasized, so I want to emphasize that in this case, because it's kind of the wisdom of many generations of chemical physicists. For example, there's a paper that shows that elastic cross-sections can be described by this model, or, reactions O plus HBr, for example, reaction in the, actually, there's a nice paper, a paper by Jan Lee, who is a Nobel laureate for molecular beams, measuring O plus Br on the related reactions. They're called light, heavy, light reactions, where there's a heavy atom, light atom, and heavy atom. This is actually a barrier, but they're perfectly well described by the universal model, which doesn't make any sense. Because there is no, there's tunneling, but still universal, this works. So this is kind of a magical / miracle thing that pops up in many contexts and it works and does not necessarily tell you why. It's kind of like a black box thing. But oftentimes complex formation is a plausible assumption and we should not forget about it. So basically exciting stuff is once you go beyond this, you become sensitive to short range effects and then all bets are off. And systems become truly different, right, from each other. And then you can control. Also, another problem with this universal is very hard to control, right? You have to have either reduced mass change or C6 change. And there's 1 over 4 power of 4 square root, right? So you have to change C6 to change the reaction rate by a factor of 10, you have to change it by 10,000. So that's not feasible, right? So there's no control, there's no room for control, there's no room for short range, there's no room for nothing in this model. So yes.
Universal model works for dimers or also
all sorts of molecules, atom-molecule collisions, dimer, for all kinds of collisions. Even elastic collisions, atom-atom collisions have been applied, and it works. Because again, it's a random phase thing. So whenever you have this randomization of the phase, you get this, but it's hard to, in every particular case, it's on a case-to-case basis, right? So sometimes you have randomization, sometimes you don't. And it has no predictive power. It just happened with KRB plus KRB, and it was great. But for example, the recent example, there is a recent paper out of the Wolfgang Ketterle group looking at sodium-lithium plus sodium-lithium collisions that observed strong non-universal effects in this sodium-lithium plus sodium-lithium. Depending on hyperfine state, the rate was below the universal value by a factor of 3 to 4. So definitely breakdown of universality is not so uncommon. And people are starting to observe it more and more as these experiments on multiple molecular collisions mature and become more kind of prominent. Okay, so my conclusion for today is you have options when it comes to molecular collisions. You can do exact couple channel calculation if you're brave enough and you have actual, good friends and electronic structure, quantum chemistry, and then you can do conversion dynamics calculations, but beware, they scale very steeply and they can become very hard very quickly as you increase the size of the system. Alternatively, you can use universal models, but then there's no predictive power. You can apply it. If it works for your experiment, perfect, great. But I'm not sure what you're learning with these universal models. So still, that's why CC calculations, and I'm an advocate of CC calculation, are still not out of business. There will hopefully be more of them, and they will be thriving. Non-universal behavior is interesting, not just because it does not agree with the universal model, but because it allows us to control molecular collisions with external fields, and it allows us to learn a great deal, hopefully, about short-range interactions in collision complexes of molecules. And I think I'm done. Thank you for your attention.
I'm curious about the point of view of wave packets dynamics, because it's shown by Kenneth that
yes,
it's used for the ultracold discovery at the wave packets have a much more robust cabinets and time for M. So I'm
it's promising. It's a promising technique because I have like very little time. I would definitely have considered wave packet techniques. Actually, now I think Chinese, there are a couple of one or two groups in China that picked up on that. From Roman was the first, of course. The problem with this kind of calculation, well, I mean, obviously scaling n squared as opposed to n cubed, so good for wave packets. The problem is that sometimes the issue is that you have to, resonances are hard to describe because you have to, propagate wave packet for as long as the resonance is. You have a resonance at least for a millisecond, for KRB plus KRB, you have to propagate for a millisecond, but how do you propagate? Your typical units are femtoseconds, which are 10 to the minus. So you have to propagate for, you cannot do it. So there are regions where wave packets are advantageous, such as light systems, maybe large molecules with not so many resonances, and it's very promising. Like something like 4 atomic systems, 5 atomic systems without heavy atoms. It's going to be the future of that. I think it's very promising, definitely. Yeah. Because it doesn't agree with the experiment oftentimes. In the cases, if it agrees with the experiment, it may be fortuitous. It may be just because of an accident, and you have no idea what's going on. That's fine. And I mean, again, don't get me wrong. I like universal models, but the whole complexity of molecules is reduced to the physics and reduced mass. You got to be kidding me. I mean, it cannot be just like that. Right? Otherwise, there would be no room for any. Like, it would be boring, right? Just calculate the rate. I mean,
of course, we're kidding. But I'll just continue the story, knowing that there are people who are universal, freed us up to look at the effects of electric fields, the effects of confinement in optical dipole traps, and to agree with all the different quantitative like that, and assess that kind of control.
It does. It does, but the key point is that you mentioned knowing that KRB is universal. How did you know that before you compare?
There it is.
Right, but you have to do an experiment. Why do you need the theory for that? Like, I mean,
right, you learn something and you use that to go.
Right. Actually, I should also not disparage. Like, the actual universal theory is not that. Please don't. Again, like, I may sound harsh about the universal theory, but actually, it's not that bad. Because there's another parameter there, it's called Y parameter, which actually can account for effects beyond universality. And people, as of recently, they've been using this extended, which is in this paper by Julian, highly recommended. You can actually include for some of that universality and back reflection of flux using this non-zero Y parameter. However, you cannot predict the Y parameter. You just basically fit, your Y parameter becomes like dependent on initial state, on magnetic field, which I think is ugly. In my personal opinion, like you just fit, right? It's not a predictive model. You just Y parameter is fit. Okay, great. But I can never be sure that if I go to other system, for example, I can use the same Y parameter. Or another hyperfine state. Can I use the same Y parameter? I'm always like shaking from with here or something like this. I will. So, but I think currently this is very promising and probably the best we can do for this heavy alkalis, anyways. So I'm not against using it, but let's say if I had an exact quantum scanning calculation, I would have done it, of course. And yeah.
I have also, as a way of clarification, we sort of universal behaviors showing the decay rate, of course, sort of fits this generic universal reality of all kinds of systems because it sort of puts all of the details of the system under the problem.
Yeah.
So, but this decay rate, it's a total decay rate. Right?
Two-body decay rate.
The decay rate of what?
It's basically two-body collision rate. KRB plus KRB measured at Gila, I think, in different internal states, -4.5. There's a nuclear spin states of ground state KRB molecules, right? In this blue squares. They basically, like they co-trap them as far as I can say, and then they observe loss as a function of time, as a function of density of molecules. Yeah. Two-body. Yeah, and yeah. So this Y, even with the Y parameter again, people were using it a lot, but it's not clear if a single Y parameter is enough to describe all scattering observables, right? It's still an open question. There's something actually we're doing research on, and it seems like for some transitions it's enough in molecules, but for some other transitions, let's say you have a reactive scattering that populates zillions of final states, you cannot describe it, all these product state distributions that people measure, for example, as a function of single Y parameter. This is what we're seeing in our calculations. You need at least as many Y parameters as you have transitions, and that's a very absolute minimum. Yeah. So this is good for total reaction rate analysis, but as your collision experiments become more detailed and state resolved, I think universal model would have to be updated and improved in order to account for this state-to-state nature.
Well, I mean, I think it's where the universality is lost because then we really need to know the details of what happens in the short energy.
No, not necessarily, because universality from the entrance channel, if you lose molecules, like you observe loss, right? It goes through many final channels, but you don't care, right? And your universal model is still fine, it's doing great. But once you start looking at state-to-state, obviously the state-to-state rates are less, smaller than the total line, right? If you're looking at a particular transition, by definition, it's not going to be universal, right? Because like Uncle Lee measured final state distribution on K2 of RB2. If I look at what happens to that particular channel, K2 forming in n equal to 5, and would be RB2 forming in n equal to 7. Obviously, the rate is going to be much below universal rate. And so you need a separate Y parameter for each transition, right? This is what essentially that entails. Yeah.
Those resonances doesn't have anything to do with the transient state. And sometimes see in chemical chemistry papers, they call these
transition state. Yeah, because you see the barrier, it's a transition state.
So it's a resonance
transition state.
Entrance state with the bound state of the
No. Well, this called tunneling resonance. I can send you a paper. Like Joe Bowman wrote a nice paper on that. And it's not because in chemistry there's so-called transition state resonance where the function is actually, it goes and then because there's a barrier, it slows near the barrier and then you get a peak in the amplitude. This all transition state resonance. It's not what it is. It's actually because collision energy is very low, it doesn't slow down, just tunnel through a barrier. And some energies you have enhanced tunneling amplitude. And the wave function is not at the barrier, it's suppressed. But amplitude inside the barrier is enhanced near resonances. So if you could measure the wave function inside the barrier, which I don't think you can, but you would see enhancement of amplitude, the particles tunneling more actively at this particular energy. So it's kind of like everywhere, but I don't know how to picture it, to be honest. Like it's just, I can send you the paper. The point is this just illustrates what you can do with couple channel content. We can discuss it more, but yeah, so it's expected, right? Because there's a barrier and you change energy levels up and down, like you're going to hit some window where you tunnel better, right? You want this coherent energy. So one example would be to look at coherent energy and then this tunneling resonance example where there's like a potential step. And then they change this K vector of the particle. It's just like simple, 1D tunneling thing. I can send you actually, if you have continuity, I can send you a page number where it is. So it's like that.
Still limited by, let's say, the utility limit times your turning rate.
I think so. Always, you're always limited by the utility, no matter what.
But you will have another suppression from the barrier that they second approximate with WKB.
Yes. WKB actually may be used to, but this barrier is not in one dimension. I just plotted one dimension because the minimum energy path, but the calculation actually accounts all degrees of freedom. So it's three-dimensional barrier. Yeah. So
it's centrifugal barrier.
It's not centrifugal, it's reaction. Yeah.
I have a question. Yeah, I have a stupid one, but
it's fine.
Follow the notation in this universal.
Oh, this is just some number. G is the identical both of the fermions. There's like 1 or 2. Yes. Yeah, I'll stop. I'll just sharing too much. I
Right. Check to see that everything is okay. It's on. Yes. Yes. Oh, okay. Now I think it will be okay. Okay.
Okay, sorry about that. Right. So what I was saying was, everything gets so much richer if we allow the molecules to come on in. And this was supposed to be. I don't know what happened with this, but this is from this wonderful paper on doing quantum magnetism with ultracold. And what I want you to take away from this is rich. And so what they have is here that considering different combinations of thermal states, right? Not just this very simple system that I identified. And in this table, this wonderful table, what they're showing is how they can control all the different parameters in these, actually what they call TJVW models. So it's with tunneling and on-site interactions. By choosing different configurations in the molecule, you can engineer whatever kind of interaction strength or Hamiltonian. That's the dream of this kind of area.
Yes, how do they model the oxygen pack? So do they think of like Hubbard constant pack?
Yeah.
Because if you say like TJ model, TJ actually projects out like that.
Yes. So I don't remember the details, but it's like that with the type one.
Okay, so it's like extended Hubbard.
Yes. Yeah. And of course, potentially a problem with these on-site interactions in terms of collisions, but you know, let's sweep that under the carpet. Okay. So the other thing we're kind of interested in is even going beyond this, right? To use this molecular rotational structure actually as a synthetic dimension. And so one could imagine actually combining many of these rotational levels as another lattice parameter. Okay? So then if I combine a spatial lattice with an internal synthetic dimension, I get a 2D system out of a 1D effect. So this is a way of increasing the dimensionality of the physics, and there are actually papers on 4-dimensional systems this way. When you take a 3D spatial system and add a 1D internal synthetic dimension. And what's the attraction of this? Well, one of the attractions is because in the internal space, the coupling, the tunneling between these lattice sites is controlled by microwaves. I can now control the tunneling on a side-by-side basis just by changing the different microwave fields. I can also change the geometry, right? For any experimentalist, that if you have one lattice geometry and then want to change to a different lattice geometry, you will know that's the one to put, right? Realign all the lasers. But in the internal space, you can change the geometry. Go from this 1D ladder. Actually, this is the SSH model we would implement to a 1D chain with periodic boundary conditions, similar pH fields, 2D square lattices. And of course, you get single-sided detection for free. You just detect which state in the molecules. And a lot of these ideas are first put forward in this paper by Kevin Hazard and his collaborators. So I encourage you to look into this if interested. On the quantum computing side, this, I guess, really stems from David Mill's seminal paper, also about 20 years ago. And I'd like to highlight this one from Kang Wen and co-workers because it's conceptually very simple. So the idea here is you would store quantum information in, say, the nucleus bins to hyperquantum the structure in the molecule. And I'll talk about that, I think, in the third lecture. And then to do a gate, promote one of the molecules, or both of the molecules up to n=1, and use this spin exchange interaction to do a gate between them. And actually, there's been amazing progress with laser-cooled molecules, optical tweezers. So these are two experiments, very recent papers from Princeton and Harvard, where they've done exactly this, done an entangling gate between molecules in optical tweezers. And what these oscillations are showing you is basically that spin exchange interaction, the hopping essentially from a spin up to spin down across from one tweezer to the other as a function of the separation of the two tweezers. So you're looking at this one over on the spin exchange. And begin that. There are more possibilities, right? So the molecule, we don't have to limit ourselves to qubits, we can do qubits. And I think this is a very much an unexplored area, but we wrote a paper on how you can do this. To do the Deutsch algorithm a few years ago. And more recently, there's been some new ideas on actually doing quantum error correction in the internal space rather than having to have many auxiliary qubits to do quantum error correction. Why not encode more robustly in the internal state? So there are lots of possibilities. That's the message I'm trying to make. So with so many possibilities, the question is, why is it so hard? Right? It's so wonderful. Why isn't the whole world working this, doing fabulous experiments? And it is actually hard. And I want to emphasize that it's hard. And actually, if you look carefully, this is why it's hard. Okay, so this is the interaction strength for rubidium cesium in a standard 10^4 nanometer lattice. So the 532 nanometer spacing that you get there. And this is only going up to 1 kilohertz. Right? This is the dipole dipole. This is why I stopped saying it was strong. I mean, it's reasonably strong, but it's not super strong, right? And what this means is you have to control all the other interactions and energy scales in the experiment to considerably better than this, right? In order to be able to see this dipole dipole interaction, which is why I haven't been very many experiments. Okay, so that's the challenge. And actually, we first produced molecules, I think, in 2014, and since then, that's basically what we've been learning how to do. It's how to engineer the optical potentials to really support long-range dipole dipole interactions without everything just being obvious. Okay. So that's the high-level fast motivation. Are there any questions on that before I take a step back and go to the beginning of the journey? Yeah.
Why does the electric field induce an icing interaction rather than, like, I guess, the strength of the experiment?
Rather than what, sorry?
I guess when you feel electric field and see the dipole, it's a lot of double factor, dipole 3. So I guess why does this finish better than I think that?
It's basically now that molecules have direct lab frame dipoles, and that kind of mimics this JZ term. That's all it is. So it's icing by. Because once you add the electric field, rather than being as this in this, let's say the rotational ground state, right? It's spherically symmetric. Now you mix opposite parity states, give slight orientation to that wave function, and now there's a lab frame dipole that points somewhere that can interact with its neighboring dipole.
And does J get larger into some larger games?
Yeah, so these two, this is the J curve. So that actually shrinks a little bit. And the blue one is the isotherm as you turn up the electric dipole. And because it has it's a difference in this case, right? It's the difference between the spin up and the spin down interaction. So if you go back to that plot of the, see if I can find it. There we go. So we're looking at the difference of this one. So this guy dips down, which is why we get that curve that you see in the direct interaction.
So you say like you have a synthetic dimension, like 100 and 110, is it like considered dimension of statement created ground as it looks like
yeah, so the motivation for the synthetic dimension is just to treat it as another lattice. And so just to think of different spatial lattice. I'm just thinking of a lattice. The molecules in n equals 1, it's in a particular lattice site. If it's in n equals 2, it's in the neighboring lattice site. And you add that to a spatial lattice, so that then it effectively makes a 2D system. Take a 1D spatial array, an internal lattice configuration. And the beauty is you're tunneling in the internal lattice. So making an optical lattice, you generally end up with the tunneling from one lattice site to the next, is all the same. But when you do that in the synthetic dimension, the tunneling between lattice sites is controlled by a microwave field. So you can have a strong microwave field for fast tunneling and a weak microwave field for slow tunneling. So you can change the tunneling rates in this synthetic dimension. That's the motivation. So it gives you more control. So in the end, you just map the rotational state onto a lattice site. That's all. Okay, so I'm going to move on. So I'm going to tell you how we make ultracold models. Right? That's going to be the journey. And let me give you what started me on this journey. So I was first, I wrote this proposal 20 years ago, kind of inspired by these kind of early papers. This great collection of theorists and said, you can create a bipolar superfluid molecules. It's really easy. Okay? What you do is you take your favorite BECs, right? In my case, rubidium and cesium, and it's kind of trivial step, you move them into an optical lattice, make this beautiful double Mott insulator state where you end up with one atom of each species on each lattice. And that's straightforward. And then, bam, convert them to molecules. They were a bit hazy on how to do that, but it's a theory. So, and it just sounded great. And actually, what they were saying was that you turn down the lattice, and lo and behold, we've got a molecular BEC, a dipolar superfluid. So this was me in 2004. New lab, no equipment, starting on this journey. I don't know if I was brave, or just stupid or naive, but this is the journey I began.
Definitely not stupid.
And as I say, my plan is
the fantastic results that will come.
yes. So the plan was to today is to start telling you about the adventures we've had along the way. Okay, filling up this lab and doing some nice experiments. So how do we make these molecules? So we can now tell you, of course, I know many of you know, but so what I'm going to tell you about is how we use a flashback resonance. I'll explain what that is in great detail. And to convert an atom pair into a weakly bound molecular state. And then this real magic step, I think, that probably, I don't know, I think it was a surprise that this worked so well, that we could actually then take this weakly bound molecular state and transfer it all the way down to the absolute ground state of the molecular potential. This is the molecule we want. This is the one that has its dipole moment and is, in rubidium cesium's case, it's chemically stable. And this process removes, again, this energy scale problem, this removes the 6,000 Kelvin binding energy in forming this molecule. And this really was, came to the forefront in 2008. These wonderful experiments in both Innsbruck and Giller, where they first demonstrated this in some homonuclear systems, but also the wonderful KLB experiments. So we've, again, I think John mentioned this separation of energy scales, this wonderful 10 orders of magnitude. So binding energy at a particular unit is huge at this point. Let's say 120 terahertz. And we could go all the way down to the translational motion, which is of the order of a microjoule, 20 kilohertz. And we have these different energy scales in between. This is what it looks like for rubidium cesium. Actually, one of my students made this in the front cover of their thesis, and I like to use this diagram. So this is where we're aiming to go from. The free atoms, of course, have hypersonic structure. This is on the kind of gigahertz scale, and as a function of magnetic field shown here. Associated with those, there are Feshbach resonances on the bound states on megahertz type scale. Down here, where we want to get to this vibration on a few terahertz, is the energy separation and the vibration. And then we've got rotation, which in rubidium cesium is like a few gigahertz separation. And then, as we'll find out in the third lecture, we've also got hyperfine structure, which is on the sub-megahertz type scale. So this is what we're trying to navigate. We'll go from these atoms all the way down to ending up somewhere down here in a hyperfine state of the point. And these experiments are proliferating, so there's many wonderful experiments around the world now. And I apologize if I missed somebody off this list, but many of you I know work on these experiments. So, as I say, I want to take everybody on this journey, so I'm going to start out really simply, and I want to explain to you what a Feshbach resonance is, and to do that, really, I want to explain, as you go right back to the very beginning, what is the scattering rate. So this is my cartoon explanation of what a scattering rate is. So, right, here's my atom. It's ultracold, so I think of it as a wave, and then I put another atom as the origin, and I get this interatomic rotation. And of course, the wave function, this atom has to adjust and it scatters off this potential, and it looks something like this, right? And the point is that here, actually, it just looks like it's been phase shifted. And I can parameterize this in terms of this parameter A, which we're going to call the scattering. It's related to this phase shift due to the scattering of this potential. And it's sensitive to the depth of this potential. I'll show you. And just to give a physical picture, so in the ultracold limit, we think of this, the cross section as being proportional to the scattering length squared. So it's like a radius of a sphere. This is the identical boson. So this is the more realistic picture, right? When you try and draw it with the right length scales, the de Broglie wavelength is enormous. Okay, so it doesn't really fit on this diagram. And then what I want to do is increase the depth of the potential. Timur showed a wonderful plot of what happens when you do this. But here, this is the cartoon picture. So as I increase the depth, of course, eventually I add another bound state. And the act of adding another bound state, I have to put another node into this wave function in the short range form. And what you see is this scattering length, which relates to the asymptote, basically goes up to minus infinity and then suddenly flips to plus infinity, right? In doing this when I add this bound state. So I can relate the scattering length to the position of the last bound state in the potential. And so if I move that, then I get this pole when the bound state is exactly a threshold, and then the bound state emerges, and that corresponds to a small negative scattering. And this is exactly what Timur was showing in this plot, where he's varying the depth of the potential and seeing all these strong wiggles in the scattering rate, the elastic scattering, or inelastic scattering. This also emphasizes why you can't just calculate the scattering rate, right? Because essentially it's sensitive to the position of this last bound state in this potential. So this potential is 4,000 wavelengths steep, right? So you need to, these guys need to do this calculation to let's say, 10 kilohertz accuracy for the whole depth of this potential, which you can't do. So when you go to somebody and say, tell me the rubidium cesium scattering, let's say, before it's been measured, then there's no answer. Can't calculate it. So how do we make a fresh drop resonance, right? So what we want to do is move that band state around. We can't stretch the potential, but with alkalis, we have other spins. So we introduce another, zoom in, and we've got hyperfine structure. And so I can take a different spin channel. And in that channel, there can be another band state, which is close now to this incoming channel. And then I add the magnetic field, and I can shift these two potentials relative to each other because they have different spins. And so I can bring this band state into resonance. And as long as I've got some change in spin coupling at the short range, I can couple across and mix in some of this band state into the collision problem. So this is shown in this slide. So what it shows is that when I play it, I will ramp up the magnetic field. You will see this band state move. Correspondingly, you get the divergence scattering length. And then this plot shows you the atomic threshold changing and this molecular band state and getting this avoided crossing when the two cross. So I played this. I made this slide years ago. I was really proud of my PowerPoint skills. And I played it and I realized I'm just asking people to look in 3 places at once. This is like impossible. So I'll play it again. Yeah. So you see this band state moving, it crosses the threshold exactly where we get this avoided crossing, and that's where we get polar scattering. Okay. So this is a real resonance, one close to my heart. This is what I worked on in it's a postdoc, rubidium 85 resonance. And I just show it because to illustrate, we parameterize these resonances like this. There's usually a pole, a width, a background scattering length, sorry, and some width to this resonance, which is conventionally called delta. And this really changed PEC physics and Fermi gas physics because this scattering length is very important piece. Right? So here, this reverse Bialkali equation and this mean field term that describes the interactions is proportional to the scattering. So Petcott resonances, being able to tune this is a great tool in being able to do this. Okay, so we're not interested in tuning the interactions at this stage. What we're interested in is using this avoided crossing to get into the molecule. So I'm going to tell you about magnetoassociation and use actually cesium, a homonuclear system, just as an example. So this is the picture we have. And as I said, to make a molecule is very easy. Just find one of these resonances, and you take the magnetic field and you sweep across it. And you follow this avoided crossing, and you end up in this weakly balanced. And you can treat this with a Landau-Zener model, and this is again from Giller, comparing actually rubidium 85 and platinum 40 in this paper. And it depends on parameters of the resonance, of course, how fast you sweep, and also the atomic density. And that's this Landau-Zener parameter. This is an important point. So all the theory diagrams I show have the atomic threshold as a horizontal line. Okay, so effectively they're all rotated like this. Okay, so the band states come up across this atomic threshold. So let's look at some of the results from this paper. Okay, so here they're varying the ramp speed, the inverse ramp speed, and just seeing this behaves very nicely to this Landau-Zener model. This plot is showing that it indeed has the density dependence predicted by this, the fact that this is a constant line. Okay. And then you can ask the question, so what limits you in terms of, if you are adiabatic, if you go slowly across this conversion efficiency is 30%. What's limiting that? And that's basically the phase-based density of the paleocasa. And that's shown in this plot here. Actually, and this is where they make this link between rubidium 85 and platinum 40, showing the same behavior. Okay. It becomes saturated slightly because as you form molecules, of course, the number of atoms left to pair up reduces. So that gives this saturation. But I want to emphasize that if you do this in an optical lattice or a tweezer where you prepared a pair of atoms, then this can just be 100% efficient. So be 100% efficient getting into this molecular state. And actually, there was a lovely experiment again in KLB where they produced these pairs of atoms actually by making a ground state molecule and taking it back so that they knew they had a pair of atoms in the lattice side. And then they can show that this efficiency is a 100% association. Okay, so this is part of cesium, cesium's scattering length. So this is the scattering length as a function of magnetic field, and these poorly resolved little spikes are actually narrow Feshbach resonances. And so to do this magnetoassociation, it's very simple. If you prepare, let's say you prepare a VEC up here, and then in this diagram, we just sweep across this resonance. Okay. And then what we're going to do is turn off the trap and apply a magnetic field gradient to levitate the atoms. And the molecules, because they have a different magnetic moment, it's basically the slope of this line. It's different from the atoms, which are this atomic threshold. The molecules with a different magnetic moment will just get a Stern-Gerlach separation. Okay. So that's what I've been explaining. The important point is in all of these experiments, we detect atoms. Right? So we always undo the formation process and just image the atoms. Okay? So you should always keep that in mind. So that's shown in this step where we break the molecule apart again and just go back across the red. So this is what it looks like. Okay. So this is the Stern-Gerlach separation of the molecular cloud, which is falling. An atomic cloud, which is slightly over-levitated, so it's rising up. And from this, you can see, you can extract the magnetic moment by how quickly the molecule falls. You can actually look at the width of the molecular cloud and extract its temperature. And in this case, you see that the temperature of the molecular cloud exactly matches the temperature of the atoms that are forming. And then you can ask, so what happens if you let this continue to fall? Right? So as it's falling, so the atoms are in a high field state. So the magnetic field on this diagram actually decreases as we go lower. Right? So the molecules are falling to lower and lower magnetic field. So what happens? What do you think happens? They're going to fall, pair the molecules in this, and then they're going to fall up. What happens here? We get to an avoided crossing, we're going to follow it. So what do you think happens to the molecular cloud when we follow it? So a question for the audience if it's not up. Any ideas? So then I've even labeled the magnetic moment change. This state runs parallel to threshold, which means it has the same magnetic moment as the atoms. The atoms are over-levitated. No, it doesn't dissociate. No. So basically, I go across this avoided crossing and I'm going to change the magnetic moment. So it bounces, right? So the atoms are over-levitated. The molecule falls initially. It reaches this avoided crossing. It follows the avoided crossing. It changes its magnetic moment. And then it goes, oh, hang on a minute, it's actually going up with the atoms, right? So it starts going up with the atoms. Then it goes back across the avoided crossing. It goes, no, I should go down because the magnetic moment changes again. So it balances. Yes, John.
The avoided crossing before seeing this, or was it a total shock? No, we knew about the avoided crossing. Yeah. I mean, you can play lots of games with these Feshbach references and the fact that the molecules are falling. So this is something that a student played with. This actually we never called it this, but this is our molecule laser, pulse molecule laser. Right? So what we did here was sweep across the resonance, and then the molecule follows this dashed line. So this is magnetic field versus time. The molecule's falling to these lower fields.
So when it falls, we can jump back across the resonance. Right? Then we can sweep again across the resonance. And we can do that many times if we get all these pulses coming out of the molecular path. Pulses of molecules coming out of the atomic PC. And what's nice about this is it really shows how the conversion efficiency depends on the phase space density. Because initially I have a BEC, so I get good conversion, but each pulse I do this, I'm depleting the BEC, and the conversion efficiency is dropping. But it gives you, what I want to show is that actually we have really beautiful control over this system, these near threshold bound states that we understand and can play. So I want to illustrate two other experiments, not from my group, but really show you some of the wonderful control that you have in these near threshold weakly bound molecular states. This one is this Tscherbul interferometry. So this is cesium again. This is actually the state of the avoided crossing we were looking at when we had the biopsy. And what they do in this experiment is go down to this next avoided crossing, which is only 15 kilohertz wide. And this is a very narrow avoided crossing. And the nice thing is, if they go down here, they can kind of split the molecular wave function into being a superposition of two different parts. So that's what they do. They go down and use this avoided crossing as a beam split. And so go across at the right speed, and you split the molecular wave function. And they have some state-sensitive detection because these G and L wave molecules dissociate very differently. When they go back up here, they get this big cloud. And if they go back up here and dissociate, they get a much tighter cloud. So that gives them this state-sensitive detection. And then you do this interferometry sequence, go down across the resonance, hold in some field, go back across, combine and look at the interference. You can very much see this interference pattern changing between these two molecular states. And we can use this to measure, actually, if you just vary the whole time, you can measure out the oscillations between being in one component or the other. And that's effectively measuring the splitting of these states very sensitively. And here they map out the avoided crossing. It's a function of energy. It all agrees wonderfully with this theory, these near threshold states. The other thing, the other tool that is nice is that sometimes you want to go across the avoided crossing, but can't because it's so wide. Okay? And then there's another trick. You're going to apply some RF to get across. And that was done in this paper that Johannes Hecker-Denschlager's group. Right? So what they do is actually, this is the experimental sequence, very, very simple diagram, but they move down to an avoided crossing, sit at 0.1, okay? And then they turn on some RF. And this RF is looping tuned with respect to the width of this crossing. And so what it does is create two new avoided crossings in the draft state picture outside of the where you're sitting. And by then sweeping the magnetic field, which is this band, they can go down to this 0.2, and this 0.2 corresponds to this lower manifold. So effectively, they're using RF to bridge the gap across this avoided crossing. And just to show how wonderful this technique is, what they did in this paper is, this is with rubidium diamonds formed at about 1,000 Gauss, and they went all the way down to zero field, and each one of these labeled circles is another avoided crossing that they jumped with RF. So we can control this this near threshold molecular state with exquisite precision, and that's important actually. You'll see it's important for being able to form the molecules. So any questions on this sort of kind of general Medina association?
So for the blue splitter at the end, as you brought up, it seems to be in principle every channel can every is that national park will choose the right wrong.
Yeah, that's absolutely true. The trouble is the right velocity this is a big avoided crossing. So the right velocity is some incredible magnetic field, which is just too high to generate. And so some crossings you're kind of forced to follow just because you can't produce a magnetic field that changes that quickly in the lab. That's why this RF comes in, because sometimes you want to go jump across, but you can't sweep the magnetic field fast enough to go across this diabatically. Let's say you just want to follow the G sector and you can't do that, so you use some RF to jump across. Yeah. That's the idea. Yeah.
Here is the coherence coefficient.
Sorry?
Going across the crossing is a coherence coefficient.
Yeah.
And then let's say the electric sphere and why you about experience is coefficient.
It's a good question. So yeah, I have to think about it. I don't think it's quite the same. But yeah, let me think on that one. Are there any more questions on the magneto association? Good. So then, in the time that remains, I'm going to actually make it more complicated by having two atoms. Right? What we're going to talk about is the experiment I built, which is this, and buried in here is one of these glass cells, and this is quite generic, I think, for this type of experiment. We have a UHV glass cell, some coils, some electrodes outside the glass cells, actives, and lots of lasers to trap and manipulate. And really, actually, so I should have put a step 0 in this making model. And I saw somebody smile when I said, you just put the two atoms into a lattice, maybe it's more insulated. Because actually preparing the ultracold mixture itself is a non-trivial step, particularly if you start out on the new mixture. Right? So I'll tell you about how we do that in this experiment. So we rely on optical trapping, and I'm sure many of you have seen this review. I'm not going to explain optical trapping in depth. I wanted to mention it because later, let's see, in lecture 3, we'll look at optical trapping in molecules, and everything, of course, being molecular becomes so much more complicated, right? So let's be clear on what the simple system is. And so as they explained in a very kind of high-level hand-waving way in this nice, useful paper, it is, you apply the optical light, and we induce a dipole in the atom, and size of that dipole depends on this parameter of polarizability. The dipole interacts with the electric field of the light and leads to this dipole potential proportional to the real part of this polarizability and the intensity of it. That's how we do the optical trapping, and how many of you do it with your labs. If you've not come across this, I want to point people to this. Many people seen this. It's a nice portal for high precision atomic data and computation. Barry Saffordova is behind this, one of the authors behind this. And this will explain, this polarizability. They've got notes polarizability. And I'll explain this in great detail. But I mean, what you see from this formula, for example, is basically there's each transition in the atom contributes to the polarizability, and it just depends on how tuned the light is with respect to those transitions. More useful is that actually you can just use this portal to do the calculations for you. And I wanted to show these very simple polarizabilities for rubidium and cesium, because really you only actually have to care about the p ions in the atom for most of the wavelengths that they're interested in. But they do allow you to do calculations for excitement state. And what we see for the wavelength we're using is that the polarizability is greater for cesium than it is for rubidium, which is going to be important. And that's important because what it means is the trap that becomes struck is deeper. Cesium is blue, so it's deeper for cesium than it is for rubidium. And so when you do evaporative cooling in this, the rubidium is going to fall out more readily than the cesium, and that allows you to do sympathetic cooling of the cesium. So very important. Gravity is important as well. In the vertical direction, it tilts the potential. It can be useful. Use it. One of the nice things with rubidium cesium is we can also cancel it for both species with a magnetic field. They have the same magnetic moment mass issue. Okay, so then you start. This is when I ask the theorists, what is the scattering rate of rubidium cesium? Of course, and then they can't tell you before you've done the experiment. So this is the landscape as we knew it when we started the experiment. So this is the cesium scattering rate as a function of magnetic field. Minus magnetic field just means we're in this magnetically trappable state. Positive magnetic field is the absolute eternal state, yeah, the one we're in. And this is rubidium 87, which is just flat and beautiful because I'm back to cooling ones. But cesium is very rich, as you can see. Unfortunately, actually, I tried to make a VEC on this side, but it's really hard because you've got a two-body loss. So forget that side of the diagram. Here, the scattering length is negative, so you don't want to make a VEC there.